Hello and welcome to the Argyle DataX Unite Data and Analytics Done Right. My name is Michael with Argyle, and it's great to have everyone joining us today. I have some information to share with you, and then we'll turn the floor over to our keynote speaker. First, a quick reminder to stop by our sponsors' virtual booths at any time during today's event and for the following week. Our partners are committed to providing you with valuable content and a great overall experience. At any time during today's event, you can visit their virtual booths from the main agenda page. These include complimentary materials, information, and meet and greet opportunities. Now, to ask questions throughout the session, simply type into the Q&A chat, and we will address your questions at the end of the session. And now, without further delay, I'd like to introduce our speaker, James Mao, PhD, Director of Data Science Principal, AI Machine Learning Research Scientist with United Health Group. We're excited to have James for his keynote presentation titled Natural Language Processing, Embedding Research and Application in Speech Recognition Models and NLP Models. James, thank you so much for being here. Welcome, and over to you.
Hi, good afternoon. I'm James Mao. I'm going to present us some embedding research and application in the ASR model and NLP model. This is my contact information, my email address, my LinkedIn information. First, as required, the disclaimer. The view expressed and the commentary provided in this presentation is strictly private and doesn't represent the opinions or work or the states of and or implementation within the machine learning and AI of my current or former employee. Any advice provided here mustn't be construed as legal advice. So a quick introduction of myself. I'm an insightful thought leader and subject matter expert in AI and machine learning with 16 years of hands-on AI machine learning research experience. I have a PhD degree and 3 Master of Science degree in the area of computer science, machine learning, and physics. I'm a first author of 1 NLP application published in IEEE in this link, and 7 patents or patentable trade secrets. My research area covered deep learning, a neural network, recurrent neural network, convolutional, NLP, NLU, speech recognition, and embedding, and semantic search engine, question-answer model, conversation AI, and the chatbot. So this is the outline of the presentation. First, the introduction to embedding research. And then there are 2 applications based on the different input format. For the sound or image format, we have a convolutional layer embedding to be used in the speech recognition model. And for the text type input, we have BERT embedding application. So this is our keywords. Introduction. So based on different embedding mechanisms, embedding is classified in a few like this: word-to-vector embedding, BERT embedding, convolutional layer embedding. And please note that these 2 embeddings, they only use dense layer as a hidden layer. And the third one, they use a convolutional layer as a hidden layer. So this will have some different mechanism for the process, because this dense layer can process the text, but cannot processing the image or sound signal. And convolutional embedding, this can deal with the sound signal and image. So we will discuss this in detail later. So based on the format, of the input, as we just talked about. For sound or image this type, we can only using convolutional layer embedding. This can be used in speech recognition model and the computer vision model to significantly improve the model prediction accuracy. And for the text, which is very common type of input, we have a very well developed BERT model. This is being very popular since year 2019, and we will discuss this in detail in this presentation. So this is a flow chart for an actual application that we can use in our business. For example, we have some speech data, which is like telephone recording. We have many telephone recording from the customer service, or maybe the customer research, or other business call. But because of the because two reasons. One is in the past, the speech recognition model, the accuracy is too low. It's only less than 80%, and most of transcribing is not accurate. And also, there were too many of those kind of recording. So I know many companies was just using this as archive, not really looking into this data. But there are many useful information inside this telephone recording. We can untap them by using the speech recognition model. So here for the speech data, we can using the convolutional layer embedding to develop deep learning speech recognition model to convert them into a searchable text. And then we can using one of these three embedding to do natural language processing. For example, we can do name entity recognition. We can do information extraction to find some useful data or insight from the telephone call or conversation. We can do the sentimental model to test whether the customer in a happy mode or in an unhappy mode, and how do we address that. And topical model, we can find what the main discussion about, and if like they have any idea or suggestion, we can pick up by the topic model. So all of these together, we achieve that by using this one of the three embedding, and with the NLP and NLU, we have get useful insight, and then we can use the conversation AI or the natural language generation. Natural language generation. We can back to this. It can have speech data output, so this can be used as virtual assistant or maybe chatbot. So actually, with the technology at this moment, this can be a very efficient and very accurate application can be developed. We can really use this kind of AI technology to make many AI automation and improve the operation efficiency by this. We can discuss this in detail later. So first, we try to discuss the convolutional layer embedding and how it's using ASR model. So convolutional layer embedding is a speech recognition an analogy to the word-to-vect embedding in the text. The word-to-vect model contains input layer, hidden layer, and output layer. Word-to-vect model only uses a dense layer and never use convolutional layer as a hidden layer. So the convolutional layer embedding was published in the IEEE journal in year 2020. It happened to be my publication, and I first mathematically derived the embedding series for the convolutional embedding, and then based on my embedding series, I developed a high accuracy speech recognition model using TensorFlow and Keras, and the experimental result is amazingly good, which it achieved an accuracy of 91.5%, which is as good as Google's speech recognition model, but my model can run much faster than Google's speech recognition model because my model is designed much lightweight. The model weight is only 10% of Google's model. So we have a very good embedding series mathematically, and also have experimental result to prove that. So I published this in the IEEE conference. In year 2020. And if you are interested in the detail, you can reference this here, and you may also email me with a question. I can answer you detail later. And so my paper differs from the Word2Vect is that I use the convolutional layer as hidden layer for embedding. While the Word2Vect, they can only allow the dense layer. They cannot accept the convolutional layer. So this is a big difference from Word2Vect. Therefore, it's called sound-to-vect embedding because it can deal with sound signal and image signal. Besides that, it can also deal with some text signal. So based on my experimental result, my hypothesis in the paper entails the convolutional layer work as a hidden layer, and the weight coefficient of the filters of the convolutional layer acting as the convolution embedding matrix. So here's the architecture I designed for the embedding. So they have input layer, which is have input the FFT signal of the sound, and they have a hidden layer, which is a convolutional embedding layer, and we have a virtual output layer between convolution and the recurrent neural network. And this one is the output layer is self-learned or encoded by machine learning by interaction between the convolutional neural network and the recurrent neural network, forward and backward propagation for many epochs. And then finally, they can get the weight coefficient to embed the sound signal into some embedding vector, some number. So we can use this to very accurately do the speech recognition, which is a very good feature extraction from sound. We only pick up the useful information from sound and get rid of those kind of noise. So this is the advantage of why the accuracy is so good. So now let's look at the mechanism on how the convolutional layer embedding work mathematically. We can define the convolutional embedding matrix E like this, which is a transpose of the weight matrix W between the input layer and the hidden layer. And then the hidden layer vector can be calculated as this, where each convolution is the function of the convolutional operation applied to E and X. E is the embedding matrix, and X is the vector of inputs. So this is the hidden vector embedded, which will be used later for final speech recognition. And then the probability distribution of a single character, yi, is defined here. Given X, this is sound signal input, the probability of y equal to yi equal to this character is like this, softmax, and w prime I, w prime j are two vectors of the weight matrix, and the T is the transpose operation of the weight vector, and H is a hidden layer vector, which is defined equation 2 in previous slide. This H. And overall, we can calculate the probability of correct, and then we using final output, use beam search to get out to find what is the final correct that match for the sound. So this is a basic principle of how the speech learning model work. And finally, the last function of the convolutional layer embedding is here. So yi hat is the model predicted value. The yi is that from model, and yi is the ground truth value in the label. Typically, the 30 characters. It's like 26-inch letter plus the space and apostrophe and unknown correct. So we try to match this one by one. So with the loss function, we can try to minimize the loss function by many epochs of forward propagation and backward propagation, and we try to find a value weight coefficient that we can minimize the loss function, and that is our final model, and we can use that to get a very good model prediction of the character corresponding to the sound input. And the convolutional embedding matrix has this structure, has N row, and N is defined as a depth of convolutional embedding matrix, which is number of filters. So in the convolutional layer, there are many parameters like kernel size and step size and padding size and number of filters. But among them, my research shows that the number of filters is the key parameter that controls the result. If you are interested in detail, I have some design rules. See, a filter must be greater than 100, then the embedding works very well. If you have filter below 20, then the embedding will be almost insignificant. Yeah, if you're interested in detail, you can look at my paper published in IEEE. So that is on the embedding serial side, and we also do the experimental result to show whether the embedding serial works. So based on this convolutional layer embedding, I designed a model, and the model result is very good. See, acoustic model only, we can get 90.2% accurate. This is a good enough accuracy. Actually, I can show the result later. And with plus a very simple trigram language model, we can get 91.5%. And if I can have luxury to put a heavy language model like a BERT model, this can get 95.3%, even much higher. So all this is a trade-off between the model weight and the accuracy, because it's very light model weight, the model runs very fast, and it's also good to be used in like a mobile phone or maybe driverless vehicle. And so for those kind of compute, we have restricted computing power. The light model has much advantage. So we trade off between the accuracy and the model weight. We can discuss this later if someone interested. And this is a real-world example of how my model works. And the upper part is a ground truth transcription of one audio file, and the bottom part is my model predict transcription. Compare these two, they are matched very well. You can see all these matched, except there are 4 arrows, which I highlighted them in yellow. Then was this then, and number 4 was 4, and main. I feel only these 4 is different. All other words match perfect. So the word error rate is 7.8%, and the word accuracy is what accuracy is 92.2%. So this result, this experimental result is confirms that the convolutional layer embedding can work very efficiently to extract a feature from sound signal, as proved in this speech recognition model. And one other important thing I want to say is that once they get the accuracy of 90%, this text is good enough to do the follow-up natural language processing. And if the accuracy is not good enough, then the natural language processing accuracy will also be poor, because garbage in, garbage out. So we want to make sure that the accuracy of the first step, which is speech recognition model, be good enough. So if we have a good accuracy like this, with about 90%, the NLP result is very beautiful. And if we have less than 80%, for example, some of these also get wrong, and NLP process will be very subtle. So this is very important, to be, this is an important trick that we have to learn, that in order to make a real application, we have to make sure the first step is very accurate, like this. Okay, so now let's go to the natural language processing part using the BERT. So a question is, why NLP is difficult? Because of some syntactic ambiguity. For example, we have a sentence, I saw a man on the here with a telescope. Without semantic context, we have a few different scenarios. For example, I'm on the here. I saw a man using my telescope. Or maybe a man on the here. I saw him using my telescope. Or maybe the other way is a man has a telescope on the here. So many different possibilities, all depend on the context. So we need context to help us to understand the whole the passage. And very luckily we have a BERT. BERT model can help us to extract those context information and understand the whole paragraph. What BERT means is bidirectional encode representation from transformer. And it's a multiple layer bidirectional. And it can be pre-trained and then be used the transfer learning for a different application. So this is a high level introduction of this. And now we have this architecture of the BERT. There are many important technical implementation inside each block, but for us, we will not dig too deep here. The only thing we need to understand is BERT consists of two parts. One is the encoder block, this part. The other is the decoder block. So BERT model combines the encode block and decode block to embedding those text input into some vectors, and later input here to use those vectors to determine whether the new input come here determines the possible. For example, there is some task like text summarization or sentimental, so it will output based on the embedding. So all of this is we convert those texts into some form of magic number, and then use this number to determine the output probability. So all this about is this, yeah. And this is a little detail about the embedding. The BERT, it contains three parts of the embedding. First is a token embedding, which is each word itself, like my dog. So this is one sentence. This is the second sentence followed this sentence, right? So this this embedding is only for this each word itself, and the second is the sentence embedding. Say this is the first sentence, one sentence, and this is another sentence, so it's marked B. So we can understand that this sentence go with this sentence. We kind of found the context relation between these two. And the third is a transformer positional embedding. This is very important because the location of this word, like this is a first word, second word, all of these will be information here. So the position, relative position information was included here and embedded so that we can use in the parallel computing to input all these words together at the same time. And the parallel computing will know that because we have position here. Otherwise, if we use a long short-term memory, which is called LSTM, they have to input the sequence one by one because they only can processing the second after the first is processed because they don't have a position. So although this looks like a trivial, but this is very important because position embedding makes the BERT model possible to do the parallel computing and calculate very fast. So we just want to emphasize that. And with this model structure, we can do many NLP things like we can do the text summarization. For example, read a whole passage and find what is the main topic it's about, and we can also do sentimental. So read the whole conversation and see whether customer is happy or not happy. So BERT model has been proved to be very successful. Get 90% accuracy for most of the NLP tasks. And here we have one example. We're using the question-answer model based on the BERT embedding. So this example is taken from the Stanford. They have a Stanford question-answer data set. And this is example say, we give the computer, let computer read the whole passage like this. And the BERT model can pretty well understand the context between each word and some relation, sequence this before, and then we can use some question to ask the computer, and actually they can do it pretty well. For example, the question of which branch of theoretical computer science, the ground truth answer is computational complexity theory, and the prediction model predict perfect. And this is the second question. They can also do it well. So basically, for the BERT model, we can achieve about 90% accurate for the question answer. So that means if you have some business document, and let's say you have 1 million of them, and you don't have time to make your analysis read one by one, so you can have this model to quickly. It can process very quickly. I think maybe few hundred milliseconds processing one. So you can very quickly processing all of these and highlight what is maybe ask them a specific question, and they retrieve that information for you, or they can tell you what is this passage about, and your analyst only need to focus on the result part of those million of passages. So this much improved efficiency, and actually some companies already using this in their real business. Yeah. So all of this is try to show you example of we can use the BERT model, BERT-based embedding to help us do the natural language. And again, we want to emphasize that in order to make the application really good, we have to make sure the speech recognition model accuracy is good enough, at least 87% accurate, like the one that I have in here. So if we get 90%, then the NLP is very smooth and result very beautiful. And if some of all these words was misspelled or using a wrong word, then the NLP totally suffer. They cannot get good result. So this is my advice to you. And yeah, so finally, I think we get it. And this is a reference. So I will put the reference number and after every passage. So if you are interested in some detail, you can go there, like this one. If you're interested in convolutional embedding, you can look into my paper published in IEEE. Or you may email me. I can answer your question later. And this is a few more reference. Okay, thank you. And question and answer.
Thank you, James, for a wonderful presentation. As a reminder, audience members can still enter questions, and we're now going to review some of the ones that came through. So James, our first question is it possible to add trigger events to speech recognition? They're thinking about interview data and creating data sets.
Yes, I think the current technology is very close to that. We can have some keywords there, and if you see these keywords, it's yeah, I think the speech recognition model has that accuracy capability. Yeah, that is yes.
Okay, excellent. Our next question, we have a couple of them the same, so I'm going to combine these two. What are some of the ways that we can get started with deploying natural language processing and automatic speech recognition, especially with limited resources?
Yes, I think there is many open source resources there. So there is some open source speech recognition model there. My model is also one of the open source, and you can find those code, and I think you can part of put the platform and then using the output in the NLP, which also has some open source. So if you have limited resource, I think I would suggest that using some open source speech recognition model combined with some natural language processing model and do some tuning and customization. The result will be very good and does not cost you much.
Excellent, thank you. Okay, so our next question, if we want to build a team, would it be preferable to grow internally or hire external for this specific skill set?
It depends. If you have some internal one who is good at the speech recognition, then I think it's totally possible to develop from internal. But some part of speech recognition still have some challenge and need very rich experience and expertise. So if hire some very good speech recognition model expert, plus and then maybe develop some NLP from internal. Yeah, so this will be, I think this will be preferred if you have no team already.
Okay, excellent. So we're about a minute, we've got about a minute left. Do you have a final thought that you want to leave us with?
So all I want to say is with the current developer of speech recognition model and NLP model, we have good enough accuracy to make a real-world application using AI for automation. Yeah, so all of this is based on the embedding. So my research interest is mainly the embedding research and speech recognition model and NLP, and combine them together to make a real-world application. Yeah, so I think this is now is totally realistic, not just like people talking about AI is far away. In the company, we can use that to improve the efficiency and reduce the cost, and also increase the accuracy, reduce human-related error.
That's excellent.
Yeah,
James, yeah, thank you so much. It was a wonderful presentation. I also want to thank everyone else for joining us today for this fantastic keynote. Now, this session, along with all of today's content, will be available on demand following the event. James, thank you.
Okay, thank you.